simulation problems you're ever going to see, my friends. This is 1750 minimum length of string after deleting similar ends. Okay, so this problem is just a direct simulation. I don't know really, I don't fully understand why it's classified as a medium. It's more so an easy, but I suppose it does really showcase your ability to program. Right, this is one of those problems where it's very easy to conceptually understand what needs to be done, but the actual implementation can be a little bit more difficult because there's these edge cases you have to consider. You kind of have to think about, all right, where are the pointers going to go? When do the pointers stop? How do I avoid, an infinite loop? How do I avoid trying to reference a spot that doesn't exist? Right? This is one of those simulation problems, although easy conceptually, more difficult to actually develop the code appropriately. Okay, and you'll see that in a moment when we start this problem. Okay, so you're given a string S consisting only of characters A, B, and C. Now, be forewarned, the fact that it's only A, B, and C, kind of irrelevant. Unless there's some solution to this problem that's more efficient, but I don't really think there could be. But the fact that there's only A, B, and C, you're going to notice in a second, is kind of misleading. It maybe will lead you to think, oh, maybe there's some other way of solving this. But honestly, the fact that it only consists of A, B, and C doesn't really matter. But anyways, let's avoid that. So you are asked to apply the following algorithm on the string any number of times. You pick a non-empty prefix from the string S where all the characters in the prefix are equal. Okay, so you take some chunk of characters from the beginning that are all equal. You pick a non-empty suffix from the string S where all the characters in the suffix are equal. Prefix meaning you take all the elements from the beginning that are equal and all the elements from the end that are equal, right? The prefix and the suffix should not intersect at any index. Okay, so they have to be disjoint from each other, right? I can't have overlap. I can't grab this much prefix and this much suffix, and there's this overlap, right? I pick a prefix, I pick a suffix, they don't touch. The characters from the prefix and the suffix must be the same. Okay, so if I select a bunch of A's from the prefix, I have to select a bunch of A's from the suffix, but they can't be the same A's that I'm selecting. Delete both the prefix and the suffix. Okay. Return the minimum length of S after performing the above operations any number of times, possibly 0. All right, so this example, you'll see, we have C and A, right? So what can I do? Well, I can pick a non-empty prefix from S where all the characters are the same, where the only prefix I can pick from S is C. Pick a non-empty suffix from the S where all the characters and suffix are equal. Well, I could pick A. Oh, but wait, the characters from the prefix and the suffix have to be the same. So there's nothing I can do here, right? Because I need to pick prefixes and suffixes, right? I need to pick characters from the start and characters from the end that are the same. And they have to be equal to each other, right? I have to pick all the same from the left, all the same from the right, but they have to be equal, and these aren't equal. So there's nothing I can do. So the length you return is 2, right? Because I can't remove any characters. So this is one of those, kind of like arbitrary, no cause, no follow through, nothing you can do kind of examples that you sometimes get. This one, on the other hand, may be a little bit more involved, so let's think about what we can do here. Okay. All right, so I have S equals CABB, CAB, AAB, AC. All right, now I'm going to pick a non-empty prefix from the string S where all the characters in the prefix are equal. Okay, so I'll pick C. That's the only character I can pick, right? So I'll pick my prefix equals C. And my suffix where all characters are equal. I have my suffix equals C. The characters from the prefix and the sum must be the same. Yep, my prefix is C, my suffix is C. And I delete both the prefix and the suffix. Okay, so I take this thing and I delete the C and the C on the end. All right. Now I play this game again. Okay, I look at my prefix. I have A. And I have my suffix equal A. What I keep putting C here. And they're equal, so I can remove those two from the system. And then I have my prefix equal B and my suffix equal B. They're the same, so I can remove them. And then here's where it gets a little interesting because I can actually remove all of them, right? Because I can remove this A. I can choose my prefix equaling A and my suffix equaling A, and then I delete both things, and then it's empty, right? So the returning string that I end up with is nothing, right? It's empty because I literally can remove everything. And let's do one more here. right. So let's play this game again. I'm not going to write s equals this. All right, so and first I could say, okay, my prefix, I could choose just a and just a, right? So I have actually options here. So this is where it kind of gets interesting, right? And this is where the nature of kind of the greedy, simulation portion of this problem becomes apparent. So it doesn't really specify how many characters I need to choose in the prefix, just that they're all the same, right? So technically I could choose my prefix being A and my suffix being A, like this, right? And then the resulting string would be A, B, C, C, A, B, B, right? But then I would have to stop, right? Because now I can only choose a prefix of A and this prefix being B. So there's nothing I can do, right? So this is not a good thing to do here. This is a bad idea. Or what I could do is I could say, well, let me make my prefix AA, right? Because I can pick any non-empty prefix from the string S where all the characters in the prefix are equal, and the suffix equaling just A. Now I would remove, they're the same, right? The quantity doesn't need to be the same, but the character itself is the same. So I can remove this AA and this A. So then I result with B, C, C, A, B, B. And then we kind of have the same situation here, right? I choose the B. Now I could do suffix equals B, and I could remove one B and one B, or I can make the suffix BB, and I could remove them both, resulting in this. And if you did this kind of thing again where you did just one, you would notice that it breaks it again and it minimizes the actual things that you can delete, right? So you want to do this, and then here I'm stuck, right? Because it's just C, C, and A, so the length is 3. Okay, so what is the point that you can derive? What is the kind of the idea here? Well, you should always maximize the prefix you should choose, right? Here we should choose as many A's as we can choose and as many A's as you can choose on the right. Because the idea here is, well, you got to get while the getting is good. That's the best way I can describe the kind of greedy approach, right? And there's probably a formal proof that you can make about why it's always, probably a proof by contradiction about why this is the optimal way of doing it. But kind of intuitively, you should get when the getting is good. And that's just an expression meaning you should take as many as you can possibly take in the moment that it's available because it may not be available in the future, right? Right now, I have an AA and an A here, right? That's the situation that I'm in. I have a prefix that's an A and a suffix that's an A. So I might as well remove as many A's as possible that I can now, right? Not removing all the A's doesn't give me any added benefit, right? If saying like, oh, I won't remove all the A's in my prefix, I'll just remove one. And I'll remove one here. What benefit does that add? Because now I just have an A again, right? And you might say, oh, well, maybe there's an A here. Maybe it's AA like this. So I could remove an A in one prefix and an A in another, and an A in the next prefix and an A in the other, right? But then it's like, well, then why do that? Why not just remove them both at once, right? In one prefix operation. So the point I'm trying to make here is there's really no added benefit to not taking all the A's that you can at once, right? If you have a prefix, you should maximize its length. There's no benefit of trying to minimize it and wait for someone else because that can only get worse, right? The best case situation when I remove one of these A's and not remove them all is that there continues to be A's. Well, if there continues to be A's, then I might as well just remove those as well. Very hand-wavy way of proving this, but what I'm basically saying here is it makes sense to think, well, the best thing I can do is get rid of as many characters as possible, so I might as well get rid of as many as possible when I can. There's no added benefit to not getting rid of all the ones that I can get rid of now in the future. It can only get worse. So you want to remove as many A's as possible when you do this. So how do we do this kind of programmatically? That's kind of the idea behind this problem, but how do we actually programmatically look at this and solve this problem? Well, one thing we can do is we can say, well, we'll start with a prefix pointer and we'll have a suffix pointer. Now we want to get while the getting is good, right? So we want to start with our prefix pointer pointing at the very left, right? Sorry. We want our prefix pointer to be at the very left because that's the beginning of the array. And we want our suffix pointer at the very end because that's the end of the array, right? Because that's how the prefix and suffixes work. So we'll say, okay, prefix equals 0 and suffix equals the length of s minus 1 because that's the index of the last element, right? Now, in order for us to remove elements, the prefix and the suffix has to be the same, right? So the prefix S, okay, S is not the right because S is here. So let's call it left and right instead. Right, so this is the left pointer and the right pointer. In order for us to remove elements, right, whatever our prefix is, the characters from the prefix and the suffix have to be the same, right? So that means that S at L has to equal S of R. Okay? S of L has to equal S of R because the elements in the prefix must be the same. Okay, so that's this condition here. The prefix and suffix should not intersect at any index. All right, so then they can't overlap with each other. So that means that L has to be less than R, right? Because if L and R are equal or on the other side of each other, right, that means they're intersecting, right? These two prefixes and suffixes can never intersect with each other, so they can never actually equal each other because that would mean there was intersection, right? So that's kind of captured here. So they both have to be the same. That's this condition. And the prefix and suffix should never intersect. Well, if they never intersect, then they're never equal, right? They're always away from each other. Okay. And then what are we going to do when we go through here? Well, remember, I'm trying to get while the getting is good, right? So if there's a character I'm trying to delete, that's S of L, right? And I'm going to just keep moving my prefix, right? I'm going to remove this A because I already know I can remove this thing, right? I know I can remove it because they're equal at their value. And then I'm just going to increase L, which corresponds to saying, okay, I can delete this A, I can delete this A. While I'm looking at the character that I'm going to delete, I'm going to keep deleting it, right? Because I'm trying to maximize the size of the prefix. So I'm going to say while L is less than R, of course, right? Because I can't go all the way to wherever R is. And L is S of L equals C, I'm going to increase L, which basically corresponds to maximizing the size of my prefix, right? I'm saying, okay, my prefix started in this position, but then I'm going to increase my prefix. I'm going to say, okay, well, I can delete one L. I can actually delete two L's. When I'm done with this, the new position of my prefix will be here, right? When I delete all the A's, my L will be in this position. So I increase L by 1, increase L by 1 again, which just corresponds to just deleting, right, these two elements. Okay? So basically what's going on here, right, the point that I'm trying to make is L and R is like I'm kind of cutting up the array without actually deleting the elements. I'm just saying, okay, the new start of my array will be here, and the new end of my array will be here at the end. So that at the very end, the length of the array is just R minus L plus 1. Okay. So L minus R, S of L equals C, L plus equal 1. And it's the same game for R, right? So we're already assuming that these things are equal, right? Because they wouldn't, if they weren't equal, they wouldn't be in this position. So while R is greater than L and S of R equals C, well, now then we can just keep going back. Like, okay, we know they're both equal here, and R will end up moving to this position here. Right, so we're saying, okay, while there's an A, we're going to get while the getting is good because we're both L seeing an A, R seeing an A, so let's remove all the A's that we see. And then we'll start at the next thing here. Right, so at this next position now we have L equal B and R equal B. So L will keep removing until it sees something other than B. R will keep removing until it sees something other than B. So R will go here. L will be here. R will go back again. And then we'll have C, C, A, and then that'll be it. And these resulting strings, right, just so you can see how this works. A, B, C, C, A, B, B, A. The resulting string from this is A, B, C, C, A, B. Actually, let's do it. Because they don't really happen in that order. You see what I'm saying, right? So these resulting strings, so this L goes all the way up to the C, this R goes all up to this. And we don't need to actually return the string, we just need to return the length. Okay. So this we subtract from R. I don't know why this got shifted over. And that's pretty much it. I think there's a 0 case we have to consider, but we'll see. Okay, so that's 2. Now this probably has an error, right? But see, this problem is more, I mean, there's an intuitive idea of like saying like, okay, there's lengths and there's, you know, we should take things as much as possible. We're kind of just simulating through this problem, right? Kind of simulating, well, the best thing to do is just to be greedy and get while the getting's good. And we're going to simulate through that scenario. But the issue with this problem is trying to write, concise, clean code that doesn't, bug out. Because it is a little bit complicated when you have these two-pointer, and that's what this problem's classified as, right? A kind of two-pointer approach. Okay. So this problem here is when it actually zeroes out, right? You're going to end up having the strings overlap. So if they overlap, then this is going to be -1, so that would be the 0 case. And there you go. All right, guys. Pretty short solution here today. Kind of wondering if you could get rid of... No. Trying to think if I get rid of this line, but I'm not going to play that game. All right. So what's the run in space? So let's say n is the length of S. So what is our space and time complexity? Well, for time, you might be pressured to think, oh, maybe it's n squared, or because, I have I go through a loop and then I loop again. But the fact is it's actually O of n. And why is it O of n? Well, L and R, you only ever increase them or decrease them. And if they ever reach each other, the loop stops, right? So I increase L, I decrease R, but the second they touch, the loop stops. So I'll never have L and R exceed the length of the array, because L is going to increase and R is going to increase, right? Like, the way you can think about it is if you have two people walking, right? Basically what this problem is, regardless of how the loop structure looks, right? If you have these two people walking, right? When they walk towards each other, right? Regardless of how they do it, maybe X is here and he takes a couple steps forward and Y is barely moving at all, right? And then maybe X takes a couple steps forward and then they hit each other and then it stops. But you notice, like, this situation, when you're walking into each other, you never exceed the length between you, right? If I'm at position 0 and you're at position 100 and we're walking towards each other, well, together we'll never walk more than at most 100 steps, right? 100 positions, because I'm walking towards you and you're walking towards me. So we're kind of confined within that space. And the second that we hit each other, we stop. So regardless of how this loop looks, right, you might be pressured to say, oh, this is n squared because there's all these whiles inside of whiles. The way that these things are actually being added together, right, the way that this condition works is the second they hit each other, they're walking towards each other, the loop stops. So it never is going to exceed the boundaries of which they exist within, and there's n spaces that they could walk in, right, because there's a length of n for S. Okay, and then for space, well, we just create these two variables, and then we create this third, variable C within the loop. So then we just keep updating that one variable. So we create 3 variables pretty much, and we use those 3 variables to determine the answer. And it doesn't really matter how big the array is, right? If the array is 10 elements or 1,000,000 elements, we still only use these 3 variables. So that's constant space, right? It doesn't matter what we do in terms of input. The number of variables we use is always the same. So it's constant. And yep, that's it. All right, guys. Peace out.